This is lecture 17 on the course Foundation of Mathematics, and we are discussing chapter 3 functions. So, in this session we will discuss the notion of inverse of a functions. So, first let us try to understand what we mean by inverse of a function through the geometrical idea. So, if we have a function say f which is going from the domain x to the codomain y, say this is the function f. So, what does it do is that it takes an element from every element from this set x to some unique element in y, okay, and if x is the element over here, when it reaches here through this f, we call it as f of x, okay. So, this f of x is the element in y. Now, inverse of this function is basically reversing a process, that is, so if this is say I call it as y. So, can we have a function which goes from the codomain of f to the domain of x, that is from y to x, such that it takes y to x, okay, and say suppose that function is g, then it takes y through g to x. So, this g of x should be g of y. So, that is called as the reversing the process. So, what do we see? What we observe is that whenever f of x is equal to y, that implies that g of y is equal to x, and whenever g of y is equal to x, f of x is equal to y. So, whenever we say that this is possible for a function, then we say that the inverse of the function exists and it has this property, Well, so the question arrive over here is that does every function has inverse, or can we reverse the function, can we reverse the process of every function? So, before getting into the answer of this, let us see when we can reverse the process. So, the first basic criteria that is required to reverse this process of a function is that the function need to be 1 1. Okay, now why this required to be 1 1? Because okay, now we need to understand that we are defining a function from y to x, and to define a function from y to x, we need to have, for every element of y, it should map to a unique element in x through this g, if I call this g as the inverse of this f, okay. And that is why if it is not 1 1, then what will happen? If f is not 1 1, then we will have a diagram something like this. We will find at least 2 points, say x 1 and x 2, mapping to a same point in y. Sorry for the incorrect diagram, say y. So, if I say that g is a function, then we will, in fact we will not be able to produce a function from y to x if this happens, because we see that this y will map to two distinct element, which is not possible in a function. Basically, you are reversing the process. So, when you say that you are reversing the process, the y should go to its pre-image. Now, in this case y goes to two different element, which is not valid in a function. So, therefore, the first condition that is required to get the inverse of a function is that 1 1. It has to be the f has to be 1 1. Okay. Now, secondly, is that enough? So, that's we see that that's also not enough. We also need the function f to be onto, because if it is not onto, what will happen? Say this is the function f. When I say that it is not onto, that means there is at least one element, which do not have a pre-image through f. So, if there is at least one element which do not have a pre-image. Again the process cannot be reversed, because I cannot define a function from y to x, because there are certain elements of y which are not mapped to any element of x, which will not be able to map to any element of x if I consider y as the domain of that function. So that's the reason, before getting into the definition of inverse of a function, we see what are the necessary and sufficient condition for to define this inverse of a function. So mathematically, to define a inverse of function, we need a function to be a bijection. If it is not bijection, then technically you cannot define the term inverse of that function. So let's formally define the definition of inverse of a function. So first of all, we need a function which is bijection. So let f from x to y be a bijection, and inverse of f is a map. It's again a function, say we call it as g in this definition, whose domain is the codomain of f, that is y, and the codomain is the domain of f, that is x, such that if f of x is equal to y, then g of y is equal to x. And this makes sense, because whenever I say f of x is equal to y, y belongs to capital Y, and so I can define a function on, I can define g of y. So g of y is equal to x. So whenever f of x is equal to y, then g of y has to be equal to x. That kind of function is called as the inverse of the given function. Let's quickly take one example to see, to construct the inverse of one particular function. So let's consider a map f from the positive part of a real line, that is 0 comma infinity, or in fact a non-negative part of a real line, to the semi-open and semi-closed interval 0 comma 1, defined by f of x is equal to x by x plus 1. So immediately one need to see whether this is a very well defined function. So x is coming from the domain 0 comma infinity. So the property for x is that x is greater than or equal to 0. One need to verify that x by x plus 1 will always be strictly less than 1, and it can be equal to 0 also. It is greater than or equal to 0. So therefore this is a very well defined function. Okay. So here I claim that this f is a bijection, and hence it has an inverse. So our aim is to find the inverse of this function. So one can very easily prove that this f is 1 1. So how is that? So I claim f is bijection, and hence it has an inverse. Okay. So first we show that this function is 1 1. To show f is 1 1. So one can start with this x1. So let x1 comma x2 be the 2 point in 0 comma infinity, such that x1 is not equal to x2. So if x1 is not equal to x2, then this implies that x1 plus 1 will not be equal to x2 plus 1, and therefore x1 by x1 plus 1 will not be equal to x2 by x2 plus 1. This says that f of x1 is not equal to f of x2, and therefore proving that f is 1 1. Next we show that f is onto, and from there itself we can find an inverse of the given function f. I cannot call the inverse because we have not yet proved that the given function, given bijection, has a unique inverse. Okay. So secondly, to show that f is onto, now we know that f is a function from x to y. So I'll take any point in y. I need to produce a point in x which acts as a pre-image for this y. So that's the whole idea, right? So if okay, now y, by the way, what is y in this case? X is okay, this is not a function. F is going from where to where? 0 comma infinity to 0 comma 1, 0 comma infinity to 0 comma 1. So let y belong to the closed interval 0 comma 1, open from the right hand side. So this implies that y is strictly less than 1 and greater than or equal to 0, right? Okay, now we want x from this 0 comma x greater than or equal to 0 such that f of x is equal to y, that is f of x is defined as x by x plus 1 is equal to y. So let's see, okay, let's extract let's see if we can have such x in 0 comma infinity. So if x if y is equal to x by x plus 1, let's try to evaluate the value of x in terms of y. So this would imply that y is into x plus 1 is equal to x, and that same as writing I want the value of x in terms of y. So evaluate this further, yx plus y is equal to x. Now take the function of y to the other side and function of x on the other side. So since this x can be taken over here as minus x, I'll take this minus y to the other side, and from here I can remove x, and what will remain is y minus 1 minus y, which is same as writing x is equal to minus y by y minus 1. That same as writing x is equal to y upon 1 minus y. Okay, now the question is this x belongs to, or is this x is greater than or equal to 0? Okay, so we want x in this interval such that y is equal to x by x plus 1, and in fact we have found this x in terms of y. Only thing we need to show that this x is greater than or equal to 0, and then we are done. So now what we know is that since y is less than 1 and greater than or equal to 0, 1 minus y, okay, from here is strictly greater than 0, right? Because y is less than 1, so 1 minus y have to be strictly greater than 0, and y is always greater than or equal to 0. Okay, so therefore y upon 1 minus y has to be greater than or equal to 0, as y is greater than or equal to 0 and 1 minus. So this implies that x is greater than or equal to 0. This implies that x belongs to 0 comma infinity. So in fact what we have done is that we have produced x in the domain such that f of x, that is x by x plus 1, is equal to y, and in that process we have also found the inverse of the function. So we have seen that whenever so if I define g of y to be y upon 1 minus y, whenever f of x is equal to y, we see that g of y is equal to x. Okay, so this proves that thus f is onto and hence f is bijection. Okay, and the inverse of the map, the function g defined from y. Okay, what is the codomain? 0, 1. I think this is open. 0, 1 to 0, infinity, defined by g of y. In fact, see, y is the dummy variable, so you can replace it by any other variable also, but make sure that you know whatever the variable that you are using, you insert it over here. So this is your g, or this is your inverse y upon 1 minus y. Okay, the reason is an inverse of f. So the reason is very simple. We see that whenever, see from here, whenever this is your f of x. So whenever f of x is equal to y, we see that x is this function which is equal to g of y. So whenever y is equal to f of x, we have g of y is equal to x, and whenever g of y is equal to I mean that is again clear from the extraction of x from y. G of f of x is equal to y. So that's how we extract inverse of a function if the given function is bijection. Okay, now the question which in fact I made a statement in while proving this, while finding this, while evaluating this inverse, the inverse of a function, the inverse of a bijection is always unique. So that's the first property of the inverse of a function. Property 1, let f from x to y be a bijection. Then inverse of f is unique. Okay, so let's produce a proof for this. So we know that f from x to y be a bijection. So whenever we want to prove something is unique, what we do is that we produce two different, we produce two, what we will do over here is that we will produce two inverses of this bijection, and we will show ultimately that this two have to be same. So let g1, okay, by the way, inverse should be a function from y to x. So let g1 from y to x and g2 from y to x be two inverses of f. So we need to show g1 is equal to g2. Now anyway, the domain of this g1 and g2 are same, as well as the codomain of this g1 and g2 are same. So only thing we need to prove is that at any points in the domain of g1 and g2 the image is same. So let me take y in y. I need to show that g1 of y is equal to g2 of y. Now since y belongs to y and f from x to y is a bijection, f from x to y is a surjective map, and therefore for this y surjectivity assures that there is a point in x which acts as the pre-image of this y. So since f is surjective, there exists x in x such that f of x is equal to y. So whenever now this g1 and g2 are the inverses, by the way I should have used the plural inverses of f. And what are the properties, or what is the definition of inverse? Whenever f of x is equal to y, this should imply that g1 of y should be equal to x as well as g2 of y equal to x. Okay. So, now since g1 and g2 are inverses of f, we have g1 of x is equal to y, oh sorry, g1 of y is equal to x. Let me erase this part. G1 of y is equal to x, as well as g2 of y is equal to x, strictly from the definition of the inverse of a function. So, what we have proved? We see that g1 of y from here is equal to g2 of y. So, we start with any arbitrary point in y, and we have shown that its image to g1 and g2 are same. So, this proves that g1 and g2 are identically same, and therefore the given bijection has unique inverse. If it's a bijection, so I am not saying that if the function has an inverse. Now, bijection naturally implies that the given function will have an inverse. So, if f, then f has unique inverse. Okay, before I wind up this session, we will see the notation for the inverse of a function. Notation. The inverse of a function of a bijection f from x to y is denoted by f inverse f to the power minus 1, okay, which is a function from y to x. So, thus if f of x is equal to y, this implies, or even the implied condition is true, x is equal to f inverse of y only for the bijection. Okay. Yeah, so with this I end up this session. Thank you for watching this video. We will have one more session, one more lecture on this concept, that is inverse of function, basically, in which we will discuss the properties of inverse of a function.